Hello everyone, welcome to lesson number 18 for BC Calculus. In this lesson we're going to talk about related rates with trigonometry. And one of the things that I'm going to stress initially for related rates with trig is what trig function do you need to use when you're solving these problems? Well, the first thing that I strongly suggest that you do is when you're reading the question, just draw the picture as you go along and then kind of figure out what we need. So we're going to do that first. We're going to go ahead and read the question. It says, a camera is mounted 3,000 feet from a space shuttle launch pad. So we don't have to be pretty cute at all with this. So we're going to go ahead and say that the camera's right here. So there's our little camera. And here's our launch pad right there. And it tells us that that's 3,000 feet of distance. And then it says the camera needs to pivot as the shuttle is launched. So think about it right now that we have our little shuttle right here, and it's going to be going up, 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 up. And so we have a camera that's on the shuttle, and it needs to kind of pivot as it moves upward. So the camera's view has to change, right? It starts out here, and then it goes here, and then here, and here. So this angle, this is our theta, this angle has to pivot. Sorry, this has to change. So it says the camera needs to pivot at the shuttle is launched and needs to keep the shuttle in focus. If the shuttle is rising vertically, all right, so vertically, that's our change in y, at 800 feet per second. So now this is going to be our y, this is going to be our x, and this is our z. We've done related rates before. Now we have a right triangle. So over here, dy dt is going to be equal to 800 feet per second. When it is 4,000 feet high, so we now know that this is also 4,000 feet. How fast is the angle of elevation? All right, so angle of elevation, you guys remember from geometry, is from the horizontal looking up. So we want to know what the angle of elevation is changing at that moment in time. Okay, so now what we want to do here is we got to figure out which trig function we're going to use. And so if you guys notice, we are given dy dt. So we know what the opposite side is. All right, we know what the opposite side is. So we have to also ask ourselves, and this is really important, what else do we know? Do we know the change in x or the change in z? Well, we know what the change in x is as well, right? We know the change in x with respect to time is going to be equal to 0 because the camera and the launch pad, they're not moving. They're not moving from each other. So what we really have here is we have the y, we have the opposite side, and we have the adjacent side. So since we have the opposite side, and we have the adjacent side, we have to think about SOHCAHTOA, right? Good old SOHCAHTOA, and figure out, okay, which of these trig functions, sine, cosine, or tangent, and it's going to be one of those three, is the opposite of the adjacent. And so hopefully you're seeing, oh, right, it's right here. So I want to use tangent. So I hope that makes sense. We're going to do example 2. We're going to do the same thing with this. So I'm going to use tangent. And I know from geometry that tangent of theta is going to be equal to y over x, right? So this is the formula that we're going to use for this particular example. Now, I'm going to go ahead and do this example the long way first by using the quotient rule, and then I'm going to go back and talk about it again where we could save ourselves a lot of time. But this is the equation. So in related rates, we always have to figure out what ties in everything that we have here. So we're going to go ahead and take the derivative of this implicitly, and so let's go ahead and do that now. And so the derivative of tangent of theta is going to be equal to secant squared theta, and then d theta dt, right? Because remember, we always have to take the derivative of our theta, and that's where we're going to get this unknown, right? This unknown for this. And then we're going to take the derivative of this implicitly. So we're going to go ahead and do our denominator times the derivative of our numerator, so dy over dt, minus our numerator times the derivative of our denominator, which is dx over dt, all over x squared. Okay, all over our denominator squared. And now we can actually start plugging in some stuff, especially to the right here. We know everything that's on the right. We now know that x is 3,000, so we can go ahead and replace that here. Usually these questions are calculator based, so you guys can use a calculator for the majority of these things. Dy is 800. Y is going to be 4,000. Dx is 0, all over x squared, and x again is 3,000. So we're going to do 3,000 squared. And again, there's going to be a little shortcut I'm going to talk to you guys about here in a little bit of time. for whatever's going on. All right, so now we have all of this. So we have secant squared theta d theta dt. Okay, so one of the things that we're going to do first is get d theta dt by itself, but we're going to simplify this down first just to kind of make it nice. So, okay, so now we just went ahead and simplify the right side to be actually 4/15. So now we're going to take d theta dt and we're going to divide both sides by secant squared, right? Divide by secant squared. So over here we have a secant squared theta that we're going to cancel out, and so we're dividing by secant squared. And so hopefully you guys realize that 1/secant is actually just going to be cosine. So then I can replace secant squared with just simply cosine squared theta, right? Cosine squared theta. And so again, just using the trig identity, that's easy for me to find. Well, all I need to know now to solve this problem is what is going to be cosine squared theta. Well, we have cosine is going to be based on SOHCAHTOA. It's the adjacent side, which we know is 3,000 over the hypotenuse. Well, we have the fact, we have the x, we have the y, so we can find z through the Pythagorean theorem. It's simply going to be 5,000, right? X squared plus y squared equals z squared. So I know that my change in theta with respect to time is going to be 4/15 times 3,000 over 5,000, which is simply just 3/5. But I'm going to go ahead and write the 3,000 over 5,000 for us right here so we can see it squared. So the change in theta with respect to time is going to be equal to 4/15 times 3 squared is 9, 5 squared is 25, and we're going to get that this is approximately equal to 0.096, and then our units are going to be radians. So theta is always a radians, and we're looking at our unit of time, which is going to be seconds. All right, so that's going to be the answer to this problem. So the first part really is just to figure out the trig function. All right, figure out the trig function, and again, you find that based on which delta x's that we know from our pictures, and then we're going to implicitly differentiate. Now, I said earlier that I was going to come back to this for a second, and so let me do so. So I want you guys to notice that in this step, right, in this step right here, that we already knew that delta x was 0, right? So I didn't really need this. And the other thing is that I could simplify, before I even did this x could actually be simplified down to this. So what I can say here is that secant squared of theta, d theta dt, is equal to simply 1/x dy dt, right? And that's the assumption, and I can do that because delta x is actually constant. So when you guys are doing this problem, remember that if a variable is constant, you can pull it out, right? So I can actually pull this out, and I can just say it's just going to be 1/x y, and then that's how I'm going to get the 1/x dy dt. So it's just a very easy way to do that. So I can go ahead and just plug in x because x is constant. You guys remember me talking about that when I'm talking. So let me actually say this in a better way. So hopefully we get this. If I ask you guys to talk about a cylinder, we talk about rates of a cylinder, we would look at this right here. We can go ahead and we can already go ahead and replace r with whatever the radius is. Let's say the radius is 3. I can go ahead and replace radius 3 because the radius is constant. Well, delta x is constant. X is going to always be constant. So I can go ahead and replace this x in my initial problem as going to be y over 3,000. So this is just going to be 1/3000y. So the derivative of 1/3000y is simply going to be 1/3000 dy dt. Okay? And I'll do another example of this a little bit later on for you guys so you can see it again in the shortcut. But hopefully that makes sense. If it doesn't, you can always use the good old quotient rule. But the point I'm making here is if something is constant, you can immediately plug it in. All right, so let's look at the last example for this video, and it's the same old story we've done before. It just kind of solidifies what we've done with this problem. Just do another example of it. So Sasha is standing on top of a 12-foot ladder. So she is standing, that's leaning against the vertical wall. So remember again, with related rates, we're always assuming that everything is perpendicular to the ground. Just so nice about that. She's standing on top of a 12-foot ladder, sorry. And we already know that the change in z with respect to time is going to be 0, right? This ladder is not going to change. This distance is not going to change. So we know that when we're looking at this, the hypotenuse is going to be part of our trig function. So we're not going to use tangent. We're looking at only sine and cosine. If Brian wants to make Sasha fall, which why would he do that? He wants to pull the lower end of the ladder away from the wall at a rate of 2 feet per second. Well, that's going to be our change in x. That's going to be our change in x. And again, it's asking us how fast is our angle of elevation changing? So we want to know what this is when the ladder is 6 feet above the ground. So when y is equal to 6, right? So when y is equal to 6. And so that's what we need to do for these problems. So if you guys look at this, and I'm going to just go ahead and make this our 6, like so, then what we can end up doing for this, ladies and gentlemen, is figure out which trig function we need to use. Well, do not pay any attention to the values that we have. What we need to figure out is what delta x's we have. If I did something with a change in x, I don't know what that is. Sorry, a change in y, I don't know what that is. So I'm having the adjacent side and the hypotenuse. So I know the adjacent side and I know the hypotenuse. So again, based on SOHCAHTOA, then I know that I'm going to be using cosine of theta. Cosine of theta is going to be equal to the adjacent side over my hypotenuse. Okay? Now, because delta z is the same, right? It's 0, I can go ahead and replace my z with 12. And that's so much nicer for us to do. So I'm going to go ahead and just simply write cosine of theta is equal to 1 over 12x. And now I'm ready to implicitly differentiate this. So yes, we could go ahead and do the whole song and dance with the quotient rule, or we can just go ahead and plug in something that's constant. So now let's look at this particular part right here. So the derivative of cosine is going to be negative sine theta, d theta dt. And then we just have to do on the right side 1/12 and then dx dt. And that right side becomes so much nicer, right? So much nicer because I know what dx is. I know dx is 2, so it's going to be 1/12 times 2, which is going to end up being 1 over 6, right? 1 over 6. So let's go ahead and look at the rest of this. So I'm going to leave the d theta alone. The negative, right? The negative for sine can just be over, well, let's leave it alone for a second. Now, what is sine? Sine of theta. Now, there's a couple of things you guys can do with this problem. You could use Pythagorean theorem, right? You use Pythagorean theorem, and when you do that, you're going to have to realize that this is going to be 6 square roots of 3. Or you can use arc sine. You can see that the arc sine, so sine of theta, let's say sine of theta is going to be equal to 6 over 12, right? Which we already know is going to be equal to 1/2. So we actually don't need to define theta. We already know what sine of theta is because we already know what this side is and this side is right here. So this is actually going to be equal to 1/2. If you had to find the actual angle, then you would use arc sine, but for this one, we already know that it's going to be 1/2 because we have the opposite side and we have the hypotenuse. And again, you could use this right here or know that this is a special 30, 60, 90 triangle and know it that way. So this is going to end up being 30 degrees and it's going to be 60, but we don't need that for this problem. Okay, we don't need that for this problem at all. All right, so all we have to do now is just start simplifying. And so we're going to multiply by -2, really is what we're going to end up doing here. So we're going to get -1/3. And again, our units are going to be radians per second. So, and this should make sense, ladies and gentlemen, that our theta is getting smaller as this ladder is falling down, right? It's getting smaller as our ladder is falling down. So again, back up to here for 1 second. I just want to make sure that when you guys are trying to find trig functions sometimes, I want to know what the sine of theta is. I can literally just look at my sides. Just look at my sides. I think that's going to be it for this first video. I want to keep it pretty short. So that's just a very first introduction to trig. I want to just say what we learned in this video is just how to figure out which trig function to use. And guys, it's going to always be, at least in this class for me, it's going to always be sine, cosine, and tangent. So we'll come back in the next video and do another problem where we're talking about theta and how that's changing, and we'll talk about that in the next. So I will see you guys in the next video.